Good evening, everyone. My name is Christine Kennedy, and on behalf of my colleagues in the Office of Alumni Engagement, I'd like to thank you for joining our first virtual talk in our exploration series. Once again, every November, we come to you. And this year, this series is generously sponsored by the McMaster MasterCard program provided by our affinity partner, BMO. So each Wednesday of the month, we bring you some fun topics. And tonight, we are welcoming a McMaster astrophysicist as we search for habitable exoplanets in the universe. So before I introduce our speaker this evening, Dr. Emma Turtelboom, I'd like to take this opportunity to acknowledge that the land on which this webinar is taking place is on the traditional territory of the Haudenosaunee and Anishinaabe nations. The territory was the subject of the Dish with One Spoon Wampum Belt Covenant, an agreement between the Iroquois Confederacy and the Ojibwe and allied nations to peacefully share and care for the resources around the Great Lakes. Just a reminder, this webinar, as always, is being recorded, and you'll get a link later this evening with also a survey, so we'd love for you to fill that out for us. And if you have any questions, we had lots of pre-submitted questions, and Dr. Turtelboom has sort of incorporated those into the presentation. But if you have any questions that you'd like to ask, we'll have about 10 or 15 minutes for you to ask those questions. So feel free to type that into the Q&A section. So now it's my pleasure to introduce our speaker for this evening. Dr. Emma Turtelboom is an astrophysicist, and she is in the Department of Physics and Astronomy. And she has been with McMaster for a few years. She's a postdoctorate fellow, and I'll let her talk a little bit more about where she studied and what she does. But we are so excited that she is here joining us this evening to talk about search for life on other planets. Thank you, Emma, for joining us, and take it away.
Great. Thank you very much for the introduction. I will go ahead and share my screen. All right. So hopefully that looks all right. Christine, please let me know if it doesn't. But yeah, thank you all so much for the opportunity to come and talk to you about the search for habitable exoplanets. As Christine said, my name is Emma Turtelboom. I'm a postdoctoral research fellow at McMaster at the moment. I moved here a few months ago after defending my PhD, which I got from the University of California at Berkeley. And before that, I did my undergraduate degree in physics at MIT. And my research is on observational astronomy, specifically on searching for exoplanets and trying to answer this really big question of how unique or not unique is our own solar system. So today I'm going to be talking about the search for habitable exoplanets with a focus on some recent results from JWST, as well as looking to the future with the Habitable Worlds Observatory. Okay, so to get started, we kind of have to start with our current sample size of one of a habitable planet, namely Earth. Of Humans have been speculating that other Earth-like planets might exist for centuries. And the fact that this could be an actual reality didn't really set in until we could see our home planet as it truly is from space. This is the famous blue marble image taken by the astronauts aboard Apollo 11, 17 in 1972. And I think this is, not only just a really stunning image, but also really gives us this perspective of our own Earth. We're really just a sort of sphere floating in the vast universe. And Earth is the only planet we know of that is not only habitable, i.e., capable of hosting life, but also inhabited. Obviously, humans, other animals, and many other forms of life. And so naturally, that begs the question, well, is there life elsewhere in the universe? And so let's zoom out a little bit first, just to our own solar system. Here, I have an image. This is obviously not to scale in terms of distances, but images of our sun and then the solar system planets. And this is from a variety of different space-based telescopes, but it really kind of reminds us that when we're trying to understand how life formed on Earth, we can not only just look at Earth, but we also need to take into account the fact that Earth is in a multi-planet system and that our solar system neighbors certainly impacted the way that Earth formed and life formed on Earth. So if we look at these images of the solar system planets here, we see that we have our inner few rocky planets, so Mercury, Venus, Earth, and Mars, followed by our gas giants, Jupiter and Saturn, then our ice giants, Uranus and Neptune, and finally, we have this dwarf planet Pluto, though that's no longer technically classified as a planet. But when we look at this sort of whole system, we can try and understand its architecture. And by that, I mean how it's laid out. We know we have these four smaller, mostly rocky inner planets. We have larger, more massive, more gaseous planets further out. And this can maybe give us clues about how the whole solar system and specifically Earth formed. For example, we know that Jupiter likely played an important role in shielding the early Earth from giant impacts, but also may have sort of funneled comets, which may have brought water to the early Earth, kind of at different points in the solar system's history. And so it's very important to understand our planetary siblings. As any of you with siblings are surely aware of, they certainly impact how we evolve. Okay. So now that we kind of have developed this understanding of our solar system over many centuries, we kind of are, of course, curious about, okay, well, what about if we go beyond the solar system? This raises a lot of questions. So we can ask questions like, are there planets that can support life in other stellar systems, around other stars? Does life exist on planets other than the Earth? Do other planetary systems look like our own solar system? Do habitable worlds exist in different types of planetary systems? Or do you really need something that looks like the solar system in order to have a habitable planet? Then, of course, we're curious about how quickly can life evolve on terrestrial planets? What are the different sort of factors that play into that? What properties of stars determine whether they contain a habitable planet? Our own sun, on the whole, is relatively well behaved. It's not a terribly active star, and this likely played an important role in life not only forming but then persisting on Earth. And then finally, is life an inevitable outcome on temperate terrestrial planets, or is it exceedingly rare? In other words, if we have all of these sort of perfect conditions that allow us to have a habitable planet, does that mean we will therefore definitely get life? And so with all these questions, there's a lot to explore, which is, I think, really exciting. And a lot of my research kind of is aiming to work towards these questions in sort of the long term. But really, what we want to do as we're sort of trying to answer a lot of these questions is try and understand which are the most promising systems to search for habitable planets, and what do we need to learn now in order to maximize the likelihood of detecting or ruling out habitability of given planets in the future. And this is very much influenced by our sort of technical capabilities in terms of what telescopes do we have, what instruments do we have at our availability. Okay, so now that I've kind of set the stage, I want to talk a little bit about the exoplanets in my talk title. So by exoplanet, you might also have seen the term extrasolar planet. But by this, I'm referring to any planets beyond the solar system. And currently, as of a few days ago, we know of more than 6,000 planets outside the solar system. And here I'm showing a plot where on the x-axis, we have the year of discovery, and on the y-axis, the number of exoplanets. And so we've only known conclusively about planets orbiting stars other than our sun for, on the order of 30 years. And you can see that, it started off slowly, but then we see these really giant leaps and bounds in our population of confirmed planets. And this was due to some really incredible space-based telescopes that I'll chat about a little more later. But now that we have this, this huge population, more than 6,000 planets and sort of growing by the day, we can start to ask ourselves these questions of, okay, we have all these planets. What do they look like? Do they look like planets in our solar system? Do they not? What do these planetary systems as a whole look like? How common are planets similar to the Earth? And is our solar system special? And kind of following on from that, is life on Earth unique? Okay, so now I'm going to talk a little bit about some of the techniques that we use to detect these planets. And this is important to understand because it very strongly influences the types of planets that we're able to detect. So firstly, I'll talk about the radial velocity method, or the RV method. This method relies on the fact that a star with a planet orbiting it, as you can see in this little cartoon here, they both are actually orbiting their common center of mass. Even though it appears that it's just the planet orbiting the star, really the star has a tiny bit of motion as well. And because of that motion, because the star is moving periodically towards us and away from us, from our viewpoint on Earth or from our telescope, that leads to basically the light that we're getting from the star shifting in wavelength, or you can also think about it as color space, over time. And so this is known as the Doppler effect. You might have come across this here on Earth when you hear or see an ambulance passing by you on a road with its siren going off. As the ambulance moves towards you, the siren is going to become higher pitched. And as it moves away from you, it's going to become lower pitched. And that is the same physics that's underpinning this method. We're just doing it with, instead of, sound waves, we're doing it from light from these distant stars. And so by looking for this sort of periodic shift in the light from a star where it's redder than bluer, then redder than bluer, we see these curves, these sinusoidal curves, which tell us that there is a planet orbiting this star. And on the right-hand side, you can see this is the actual data that was taken by Mayer and Kellogg, who recently won the Nobel Prize for this discovery of 51 Pegasi b, which was the first exoplanet orbiting a main sequence star, or a sun-like star, that was discovered in 1995. And you can see this sinusoidal, so up and down motion, which is characteristic of this method. And using this method, we can learn a planet's mass and its orbital period. And so if we do this for many, many planets, like I said, we have this population of 6,000 confirmed planets, we can kind of put them all together and see what we find. And so that's what we're doing here. On the x-axis here of this plot, I'm showing semi-major axis. You can think of this as the distance from a planet to its host star. And on the y-axis, you can think of this as being planet mass. And so here again, I'm showing the solar system planets with their little images with the blue crosshairs on Earth, where again, if we're looking for habitability, we want to look for an Earth analog. But now let me add the radial velocity detected planets. And I'm showing those here in black. And so we can immediately notice that, one, there's a lot of them. That's very exciting for someone in my profession. There's lots of data to dig into and try and understand. But also, they seem to be in an area of this plot where we don't see a ton of solar system planets. We see some of these detected planets as similar to Jupiter or Saturn, but most of them are either more massive than the solar system planets or closer into their host star than the solar system planets. And this was a very interesting result. Okay, so now that we've talked about radial velocity method, now I'm going to chat about the sort of second workhorse method for detecting exoplanets, and that's the transit method. This method depends on the fact that some planetary systems are aligned in such a way that a planet will pass between its host star and the Earth, sort of along our line of sight. This is not the case for all planetary systems, right? We need to have this sort of correct alignment. But if this alignment is present, then as the planet passes between its host star and our telescope or our eyes, it blocks out a little bit of that star's light. Now, we can't see the planet directly. This is the same with the radial velocity method. Planets are typically much smaller than their host stars, much fainter, and so we're typically not able to resolve them with our telescopes. But what we can see is the effect that the planet has on its star. And so as it transits, it leads to this periodic dip in the stellar brightness, which you can see in this cartoon, and then in some real data on the right-hand side for HD 209458b. It's one of the early transiting planet detections. And so when we see these periodic dips, that tells us that, oh, there's a planet around this star. And from these measurements, we can again get the orbital period and then also the planet's radius. So let's now add this to our population. Let's see what these transiting planets look like. All right, and so I've added them here now in purple. And so again, we see that they're typically, pretty close in to their host stars. They have small separations and that they're also fairly massive. So I'll also note that the axes on these plots are logarithmic, meaning that so 10 to the 0 refers to 1, 10 to the 1, 10 Earth masses, 10 to the 2, 100 Earth masses, etc. But so the planets we're finding through the transit method, they're typically closer in than Earth, and they're also typically more massive than Earth. Okay. So the final method I'm going to discuss here, there are others, but these are kind of the main ones that are relevant for our discussion today, is direct imaging. Now, the name is pretty self-explanatory here. It's directly taking a picture of a planet. And here on the right, you see this sort of little movie showing the HR 8799 system. I wish a lot of these stars had more exciting names. A lot of them are these sort of long numbers. But this is a really exciting multi-planet system that was directly imaged by Jason Wang and Christian Moreau. And you see this beautiful image where in the middle we have where our star is, HR 8799. But in this case, it's covered with this sort of circular mask, which is blocking out our starlight. And then this is a movie, so temporally you should see these 4 dots, 3 on the right-hand side of the star and 1 on the left, that are our planets. And you can see them moving around the star in these little circular orbits. And we don't see the full orbit, but we see parts of it, which is really amazing. Now, this is a really challenging method. It's not as easy as it sounds. For a bunch of different reasons, but namely, as I mentioned before, planets are typically a lot smaller than their host star and they're a lot less luminous, a lot fainter. And so right now, direct imaging is really only possible for far out planets that are giant, so Jupiter-sized or above, and are young, which means that they're still quite bright. And the reason for this is because the host star is just so bright. And we use something called the coronagraph to try block out the host star's light, but it's a really technically challenging problem. You can think of, if we want to directly image a planet like this, it would be like trying to distinguish a firefly next to a sort of street light, like a lamppost, in Toronto, if we're standing here in Hamilton. And so you can imagine this is a very challenging thing to do. But this is another method that we kind of have in our toolbox when we're out looking for planets. And we find that a lot of the planets found through direct imaging, shown here in red, are, again, these very massive, distant planets. Okay, so now we're looking at this plot, we might be asking ourselves, where are all the exo-Earths? Where are the Earth-like planets? This is not boding well if we're on the search for an Earth analog. Now, something that I haven't mentioned yet, but which is really important to understand, is our sensitivity biases. In other words, what planets or what types of planets are we sensitive to detecting? And what we find is here I've kind of added sensitivity curves for a bunch of these different methods that we discussed. But if you look, for example, at the imaging, sort of the red lines added there in the top right, all that's saying is that using this direct imaging technique right now with our current technology, we can only really find things that are very massive and far out. Similarly, with radial velocities or RVs and transits, we're really only sensitive to things that are close in and relatively massive, though we're kind of pushing down to smaller and smaller planets with more data and more advanced techniques. And so you can see that a lot of the solar system planets fall outside of these bounds. So in other words, just because we haven't seen them doesn't mean they don't exist. It means that right now they're at the edge or just beyond our sort of detection capabilities. However, even though we're not necessarily sensitive to detecting Earth-like planets at the moment, what we can do is extrapolate and try sort of get a picture of the true underlying occurrence rate of planets from the planets that we can observe. And so this is something that has been done extensively with the results from the Kepler mission. Kepler was one of NASA's flagship missions that really revolutionized the field of exoplanet science. It discovered sort of thousands of planets via the transit method. And specifically, the aim of this mission was to look for transits of Earth-sized planets around sun-like stars, right? That's kind of what we're interested in, at least at first, when we're trying to answer this question of how unique is the solar system? How unique is Earth? And so from the results from this mission and a lot of work by a lot of different people, we found that the typical estimates, we think, are for Kepler, for stars in the Kepler field, that we have about 0.25 Earth-sized planets in the habitable zone of their stars per star. And so what that means, I'll go into more detail about what exactly I mean by the habitable zone in a little bit, but for now you can just think of it as the name suggests, a region of parameter space, in this case, separation from the host star, that is potentially favorable for hosting habitable planets. And then of course, Earth size, that's what we're interested in here, around 0.25 planets per star, which is, not nothing, but, we're not seeing one. It's not around every single star. And we might think, oh, well, 0.25 is still great. Kepler looked at, hundreds of thousands of stars. Presumably there's going to be loads of these exo-Earths flying around. Let's go look, get more data. Let's understand them better. Let's go look for these exo-Earths. However, a lot of the Kepler targets, unfortunately, are poor targets for mass measurements because they're quite faint, and specifically for atmospheric characterization. And so now I'm going to talk a little bit about what does it mean for a planet to be habitable? What measurements do we need to take to try and understand if a planet is habitable? So habitability is, a measure of an environment's potential to support life. Again, we have our sample size of 1 on Earth, and our understanding, broadly speaking, is that life on Earth requires and slash required to form a liquid solvent, in our case, water, energy, so stellar irradiation, elemental ingredients. So here I'm showing the chemical notations for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and then appropriate physiochemical conditions. And so what I mean by that is we need the right temperature, the right pressure, as well as the right ingredients, as well as a liquid solvent, as well as energy. And we kind of throw that all together, and through certainly complex chemical reactions that I'm not going to go into, but we eventually end up with the sort of complex life that we see on Earth now. Sorry. Okay. But this is sort of just a first pass at what I mean by habitability. When we really try to dig into, okay, what does it mean for a planet to be habitable? We find that there's a whole host of factors impacting habitability. I won't go into all of these just for the sake of time, but we can kind of group them into different components. So if we look at the sort of bottom half of this graphic first, these are our planetary properties, as I mentioned for Earth. What sort of structure do we have? What composition do we have on our planet? Do we have plate tectonics like we do on Earth? Is that necessary for habitability? What is our atmosphere doing? This is really, really key. What elements do we have in our atmosphere? Does our on Earth, for example, we have our atmosphere, which we have this greenhouse effect that keeps temperatures on Earth fairly stable, which is very important. We also, for example, on Earth, we have seasons. The Earth orbits the sun on a slight axial tilt, and so we get seasons. What does that mean for habitability? On Earth, we have these large oceans, but then we also have large areas of land. Can life develop in the ocean, then migrate onto land, migrate back? These are all sort of possibilities. But then when we move beyond just the planet itself, we also need to take into account stellar effects. So some of these are shown in the top left here. How does our star impact habitability? Our sun, we know, has sometimes coronal mass ejections and other sort of activity which results in these really super highly energetic particles being emitted. And that could really be an issue for life, developing life. Thankfully, our sun is quite quiet on the whole, so this isn't too much of an issue for us here on Earth, but that might play a big role in other solar systems. And then finally, again, we have to take into account the fact that these planetary systems are multi-planet systems. Thinking about how often are we getting, for example, meteorites, which we know led to a large extinction event on Earth. How stable is our planet's orbit, and which can be perturbed by other planets in a system. There's so many things going on which are all really exciting to try to understand, the role they play on Earth and try extrapolate that to beyond Earth. But also means that there really isn't a sort of simple equation that we can make to understand if a planet is habitable. We just are trying to put together all these different puzzle pieces. And so with that, I now want to introduce this idea of the habitable zone, which I mentioned before. And this is really a starting point to evaluate the habitability of a planet. We know that on Earth, at least as far as we understand it, we need liquid water to sort of have life form and be sustained. And so when we're looking at extrasolar planets, we can try and see whether the light, the radiation that a planet gets from its host star is sufficient to support liquid water on a planet's surface. And so you don't want a planet to be too close into its host star because it's going to be too hot. Don't want it to be too far out because it's going to be too cold. You might have also heard this referred to as sort of the Goldilocks zone, right? You want it to be just right where we're able to have liquid water. Now, this is all well and good, but as I said, this is really just a starting point. Because, for example, again on Earth, we have our atmosphere, and through the greenhouse effect, it really regulates our planet's temperature. And so just looking at the incident radiation from a planet's host star is not enough to understand whether or not liquid water could persist. And so in order to try and understand this, we want to try and look and measure the atmospheric composition of exoplanets. We know that on Earth, our own atmosphere contains a bunch of different molecules. Predominantly, we have nitrogen. This came from volcanism at earlier times in the Earth's evolutionary history. We have oxygen. We know that's required certainly for life as we know it. We have water vapor, which points to a water cycle containing liquid water from our oceans that then evaporate and then rain out as rain. And then there's obviously other gases like carbon dioxide, argon, what have you, ozone, etc. And so in order to try and understand this about exoplanets, we need to kind of use a bunch of different techniques to, on Earth, it's relatively speaking quite simple. We can, send up weather balloons. There are also, things are more tactile. They're closer at hand than in these exoplanetary systems where we're never very unlikely to ever be able to sort of journey and go measure in person. And so the technique that we use predominantly is known as spectroscopy. I sort of mentioned this earlier in the context of the radial velocity method, but really all spectroscopy is splitting light into its component colors, or you can also think of it as wavelengths. And we see this frequently on Earth in rainbows. And so we can do this as well from light from stars. Here I'm showing a spectrum of the sun, I believe, from 1877, which is really quite astounding. But you can see you have this rainbow gradient of the light that's been split up into its component colors. But you can also see there are these dark bands. And those are absorption features that come from the fact that in the sun's atmosphere, there are certain molecules that basically absorb certain wavelengths, certain colors of light, and don't allow them to pass and reach our telescopes. And so by looking at an absorption spectrum like this, we can try and understand, or this can give us a clue as to the composition, what elements, what molecules are there in whatever it is that's emitting this light. This technique is used very broadly in astronomy in a bunch of different ways. But in the case of exoplanet atmospheres, we apply it in something called transmission spectroscopy. And so what this technique relies on is when a planet transits, so again, when that planet passes between its host star and our telescope, so along our line of sight, light from its host star is going to pass through the planet's atmosphere on its way to us. And as it passes through that atmosphere, some of the molecules in that atmosphere are going to, again, absorb certain wavelengths, certain colors of light, leaving this characteristic sort of imprint on the spectrum that we then measure with our telescope. And from this, we can try and back out what those molecules are. So here I'm showing sort of some more, a model of Earth's atmosphere, Earth's transmission spectrum. On the x-axis, I'm showing wavelength. You can also, again, think of this as color with red towards the right, blue towards the left. And then the y-axis is the light blocked. So these features, and by that I mean these sort of spiky bits of the spectrum, relate each to individual molecules that are blocking these wavelengths of light. So you can see in our own transmission spectrum, we see oxygen, we see carbon dioxide, we see water lines, we see methane lines. And this is a way of kind of looking at the chemical fingerprint of a planet's atmosphere. So now let's talk about what this looks like for exoplanets. This is for Earth. Let's look at it for exoplanets. So this is the first transmission spectrum released by the James Webb Space Telescope. Is of WASP-96b, which is a highly irradiated planet, so it's very close into its host star. And again, it's on the x-axis we have our wavelength, on the y-axis we have the light blocked, and in the white points are our actual data, and then blue is our model. And what we can see is these beautiful water features. And this is really exciting. It tells us, great, there's water in the atmosphere of this exoplanet, of WASP-96b. But this type of observation can also let us probe a lot of other types of molecules, but it can also let us try and understand, are there clouds on these atmospheres? At what height are those clouds if they are there? There's a lot of chemistry that goes into a given atmosphere. And so taking this data allows us to try like disentangle all those pieces. Now I'll also mention that these spectra are they're very complicated to interpret, right? As I said, there's a lot of different physical processes going on. And so it's really exciting to get all these data, but a lot of the time they sort of raise more questions. And they're like, okay, well, if we have this molecule, how does it make sense with our understanding of the host star and how close in the planet is orbiting and things like that, which is really cool. But with this technique, we've been able to learn a lot about exoplanet atmospheres, and particularly about the atmospheres of planets that really don't look a lot like Earth and like solar system planets, which is really cool because we don't have any analogs for them in the solar system. And so we're probing entirely new types of atmospheres, which is very exciting. But if we kind of pull it back to our original question of, trying to search for an Earth analog, that's still really, really hard to do. To find a true Earth twin around a sun-like star is really hard. So showing this plot again of our confirmed planets and our sensitivity biases, you can see there's really not a lot in this regime near Earth. There are some if you're willing to go to higher masses, this is 10 times the mass of Earth. And certainly we're pushing towards it, and a lot of really smart people are doing a lot of really hard work to try and get here, which is just really exciting to me. But there's still a lot to be done. And so looking to the future, we know that Earth-like planets around sun-like stars have very small detection signals. So we really need to have high precision instruments to be able to detect them. We also, I haven't really talked about this much, and I won't for the sake of time. If you're interested, I'm happy to answer questions about it. But we also need to take into account the fact that stars vary, and that can really obfuscate our interpretations of planetary signals, especially when it comes to exoplanet atmospheres. And so a lot of the time people say this phrase of know thy star, know thy planet. In order to understand any given exoplanet, we really have to have a good understanding of its host star. And similarly with the solar system, there's still a lot about the sun that we don't know. And there's a lot of really interesting research going on trying to understand specifically stellar activity on the sun, which is very cool. But we need extreme precision RVs. the precision needed to detect an Earth-like planet orbiting a sun-like star is very, very small. It's on the order of 10 centimeters per second. And the sort of state-of-the-art instruments at the moment have comfortably passed a meter per second, so 100 centimeters per second. But it's really challenging to get down to the precision we need to detect an Earth-like planet around a sun-like star. And then, of course, if we want to look at the full orbit of such a planet, it takes a year, right? And we want to see a couple of them to build up our signal to noise to make sure our observations are reliable. So these things take time. We also need precise space-based photometry to detect these transiting planets in the first place. And so Kepler has now been decommissioned, but we have the TESS mission, which is currently ongoing and is really continuing a lot of that work. We need ground-based ELTs. So ELT stands for Extremely Large Telescope, not the most inventive name, but does very descriptive. These are sort of the next generation of telescopes, which are really going to allow us to hopefully get to the precision that we need. And then all of this put together, when we try and expand our sample of confirmed planets, expand our understanding of these systems and their architectures, how they're laid out, what their host stars are doing, we can then try and really push towards finding an Earth-like planet. And so with that, I'll now talk a little bit about the Habitable Worlds Observatory. This is a concept, a mission concept, developed sort of through the Astro 2020 Decadal Survey that would potentially launch in the 2040s. And it was sort of conceived through this Astro 2020 Decadal Survey, which is sort of put on by or like solicited by the National Academy of Sciences, Engineering and Medicine every 10 years, as Decadal suggests. And sort of the idea here is for sort of the leaders of the field to identify, okay, what science questions are we really excited about answering, and what technology do we need to develop to get there? And so in the case of HWO, the sort of vague design that they put forward is we need a large aperture, i.e. a big ultraviolet, optical, and near-infrared space-based telescope to perform transformative astrophysics. And so it's called the Habitable Worlds Observatory, and kind of one of its main tasks would be to search for signs of life on planets outside our solar system. But HWO would very much also enable a whole host of really exciting astronomical discoveries, not just in exoplanet science. Okay, and so here is a simulation of what the Habitable Worlds Observatory could possibly see if it were to look at our own solar system. So we're directly imaging the reflected light from these planets. Here you'll show it, we're seeing Mars there circled as this sort of little movie keeps playing. You can see some of the different solar system planets. And so this is kind of the goal, is that we would want to image and then take spectra, direct spectra of 25 Earth analogs in order to search for biospheres. Now, again, this is really challenging. This is why we're not doing this right now. We still have a lot of work to do to get there. One of the key challenges is the flux contrast we need. So if you remember that example I gave of a firefly next to a lamppost, in this case, think of something 1,000 times fainter than a firefly. So really this tiny, tiny pinprick of light that we're trying to detect next to a blazing street lamp. So currently our kind of state-of-the-art instruments are able to do around sort of 10 to the -8 flux contrast. We need to get 10 to the -10, so 100 times better. We also want to look close in. As I mentioned earlier, direct imaging at the moment, we're really only sensitive to things at tens of AU, so 10 times the distance of Earth from the sun. But if we want to detect an Earth analog, we have to get to 1 AU, or the same distance as the Earth from the sun. And so there's a lot of work to do to get us there. But if we can do it, and I think we can, we'll be able to not only directly image, but then get spectra of these Earth analogs. And so again, this is a simulation of what the modern Earth might look like as observed by an HWO-like instrument. And from this spectra, we can see a whole bunch of physical processes. We see Rayleigh scattering, excuse me, which is why our sky is blue. We see water features. We know we have, water on Earth. Of course, it's very important for life. We see evidence of oxygen in O2 and ozone, O3. We see carbon dioxide from volcanoes. And so there's a bunch of these both biological and abiotic signatures that we can see in an atmosphere that we can probe with this spectra. And then comes the challenge, but also the exciting challenge of picking those apart and trying to understand, okay, which of these can only be explained by life? And which of these have other explanations? And what do we think the relative likelihood of those scenarios are? Now, another thing that we need to consider is that atmospheres vary with age. Again, we have the most in-depth understanding of the Earth, and we know that the Earth's composition and therefore what it would look like as sort of spectra taken from afar is going to vary with time. And so we know the Earth is, roughly 4.5 billion years old. We know that life evolved, different types of life evolved at different times in that history. And we also know that the Earth's atmosphere, and therefore our observables, the things that we would actually be able to detect with our telescope, are going to look different. And so here I'm showing this plot on the lower right is an example spectrum of Earth as it currently is. And so we see labeled a lot of those O2 and O3 features, excuse me, as well as H2O. We know there's oxygen in our atmosphere. We know that's important for life, H2O as well. But if we sort of dial back the clock and go to the Proterozoic Earth, where it's believed that there was between 0.1 and 1% of the oxygen that we currently have, this is going to look quite different. And specifically, the thing to note here is that a lot of the O2 features, so just pure oxygen, are not visible because there's so much less of it. There was so much less of it in the atmosphere at that time. And so if we were to have looked at the Earth at this time in its history, O3, this oxygen feature, which is, there's only one of them in this spectrum, would really be our only way of seeing that there was oxygen on this planet. And so you can see that it very quickly becomes quite difficult to tease apart, like, okay, what are we actually seeing here? And then these are also models. So of course our data is going to have some noise, some scatter. And so it's a very complex sort of investigation. And then if we dial the clock even further back, there we go, the Archean Earth, we see the atmosphere looked really quite different. We see a lot of methane features, that's CH4, as well as H2O. And then we see the effect of this potential effect of this haze, this sort of cloud-like layer. And we see the impact of these hazes on exoplanet atmosphere observations already with JWST, where really the effect of a haze is to flatten out a transmission spectrum, where it basically masks all of these features because you basically have a cloud deck that is covering up a lot of the atmosphere. And that really, if you'll pardon the pun, clouds our ability to understand the atmospheric composition of these planets. And so not only do we need to try disentangle those things, we also need to take into effect this temporal variability. And what this tells us is we also need to be doing a lot of work, not only trying to understand exoplanet atmospheres, but also understanding our own Earth, understanding the evolution of the other planets in our solar system, and modeling a lot of these. Okay, well, what would Earth have looked like under these conditions? And how might we be able to infer that a planet was habitable if we had that information? And so all that is to say, to kind of sum up, that there are many, many steps to determining habitability. And it's not a super simple equation, unfortunately, as much as we might like it to be. Here I'm showing sort of, this is a technology flowchart, but the sort of science questions driving this are on the left-hand side. So firstly, when we're considering any given planet, we have to look at its host star. Is it promising? Do we know that it's a single star, or does it have a binary companion, which really would potentially mess with the formation of planets? Then, once we have a star that we think looks promising, we can go look for planets, for exoplanets. We can stare at it, we can use transits, we can use RVs, we can use direct imaging, what have you, and try and understand, okay, are there planets around it? And then we have to be sure, well, is it actually a planet? Could it be a false positive? Could it be something else that looks a little bit like a planet in our data, but isn't truly planetary? Then, of course, we want to know, is the planet in the habitable zone? And what is the habitable zone? There are many different definitions of the habitable zone depending on sort of what physics you're including in it. Then we want to go searching for water. That's kind of our first sort of most promising avenue for a biosphere. And we can do that again with our atmospheric transmission spectroscopy. We also need to take into account, what's the star like? Does it have a ton of really explosive, energetic flares, which might have wiped out life, even if it did form? How massive are the planets? If we have something like Jupiter or Saturn, which is, really massive and doesn't have a surface in the same way that Earth does, do we think life could form there? Maybe, maybe not. It would have to look quite different to life on Earth. And then finally, we can ask ourselves, are there signs of life? Are there these biosignatures, these different molecules that we think are related to biotic processes? We want to make sure those signs of life are robust. We don't want to get too excited too early. We want to create a full picture of a planet's atmosphere. Look for other features, try get a sense of the sort of global picture of that planet's atmosphere. And then we want to revisit this. We want to look at this again and again and make sure this is what we're seeing. Are we seeing variation due to seasons, for example, if this planet is tilted? And with all of that, we can then maybe put together a picture of how habitable this planet is. And so this might seem a little bit disheartening. There's a lot of work to do, but I also think it's so exciting to try and not only kind of think in the big picture of sort of what might life look like, where might life have evolved elsewhere in the universe, but then also like come up with these sort of quite concrete methods and checks that we need to do of any given planet to try and answer that question. And so with that, I'll leave you with this quote from the Decadal, as well as another beautiful image of Earth taken from the moon. If planets like Earth are rare, our own world becomes even more precious. If we do discover the signature of life in another planetary system, it will change our place in the universe in a way not seen since the days of Copernicus. So with that, I'll thank you all so much for your attention, and I'll be happy to answer any questions you might have.
Thank you, Emma. Wow, that was fantastic. We have lots of questions coming in, so I'll get to those. I guess the one question that I have, since I'm the host, I get to ask the
Exactly.
question. So this Habitable Worlds Observatory,
Mm-hmm.
obviously that's not now. Like when
Mm-hmm.
is that? When is the hope that something like that
Yeah.
would be available?
So the kind of hope laid out by the Astro 2020 decadal is that it would sort of launch in around the 2040s, somewhere in that decade. That's obviously dependent on the sort of maturity of the technology, whether we have the instruments capable of doing the measurements that we want. Then, to get more granular, you have to take into account things like launch windows. When is it feasible to launch a facility like this? And so there's a lot of different things that go into it, but the sort of broad aim is the 2040s.
And how far it would go further than where Kepler is?
So again, HWO currently, so Habitable Worlds Observatory, is currently a mission concept. So that means that we have the decadal sort of combined results from these different mission studies and said, we think in order to answer these science questions that we think should be prioritized, we need to have a telescope that is bigger than Kepler. It's going to be a lot bigger than Kepler. And it needs to have these technical capabilities. There are many, many, many of them that I won't go into. Um, but yeah, the idea is that it will not only be able to look further away than Kepler, but then also have higher precision and also be able to take spectra, which Kepler wasn't able to do.
Oh, right. Okay, great. Well, thank you. That is exciting for anyone who is studying what you're studying. That is obviously
Yeah,
um, something that people are looking forward to. Sorry. Okay. So
absolutely.
I'm looking at all the questions here. Okay. So uh okay, so this is about the transit method. So Simon
Yeah.
is asking, with the transit method, how do you know the angle of alignment? Exactly at the middle,
Yeah.
0 degree, but in reality, different as you explained.
Yeah, that's a great question. So the question is for, as I understand it, for the transit method, we have to have this sort of fortunate alignment of the planet along that passes along our line of sight as it orbits its star. And so the fact that we do see a transit, we can constrain geometrically the range of inclinations, which that term refers to the angle between our line of sight and the plane of the planet's orbit. We can measure that from the transit itself. So kind of from how long it lasts and how deep it is, we can back that information out. But you're absolutely right that we assume that the universe is not favorably aligned for us to detect planets. We assume they're oriented in all directions equally. And so there are many, many planets that we're not going to be able to detect with the transit method simply because their orientation is not favorable.
Okay, great. Thank you. Peter is asking, now we're going to the Doppler effect.
Mhm.
For the Doppler effect method, is the angle between the plane of the orbit and the line of sight determinable, and or what impact does it have on the conclusion?
That's another great question. So it's not, we're not able to determine eye inclination from the radial velocity method. And what that means is that the mass that we measure, which is taken from the amplitude, so the height of that sine curve that we see in the data, that means that that's really the minimum mass of the planet. It's not a true mass because you might imagine that if because we're measuring with this method, we call it the radial velocity method. And radial there refers to the fact that we're only able to measure the component of the velocity along our line of sight, i.e. the radial component. And so depending on how inclined the planet's orbit is, we don't know how much of what other component we're missing. And so what that means is that masses measured from the radial velocity method are minimum masses. However, if a planet also happens to transit, then we can remove that degeneracy and measure a true mass.
Oh, okay. Thank you. So
Yeah.
hopefully that answers Peter's question. He did have a follow-up question.
Yep.
In the atmosphere mass, where is the nitrogen and nitrogen compounds?
So if you're referring to some of the examples of the transmission spectra that I showed, and you're curious why you didn't see nitrogen compounds like NH3 ammonia, for example, in them, that is to do with the wavelength region that different instruments can probe. We can see some of those features, they just happen not to be in the examples that I showed.
Since we're talking about those
Mhm.
spectrum, so you're obviously looking for sort of the compounds that are similar to compounds that are on Earth, if we're
Mhm.
looking at habitable exoplanets.
Yep.
But are there any exoplanets that are similar to our other solar system planets?
Ooh, that's a great question. Yeah, so that is something that I think that I'm not an expert on planetary science, so I'm not as familiar with exactly what we know about the other solar system planets. But my understanding is that based on our knowledge of, for example, Jupiter and Jupiter's atmosphere, we can try and compare it to Jupiter analogs in other exoplanetary systems. The issue with trying to look for, say, a Jupiter analog is again that they're quite far out, and for transmission spectroscopy, it's really favorable to have things very close in. We're typically looking at exoplanets that orbit their stars on the order of, call it 1 to 30 days. So they're really whipping around very fast. For comparison, Mercury's orbital period is 88 days. And so, really, just the chemistry that we see in the atmospheres of those exoplanets, because they're so highly irradiated, because there's so much radiation coming from their host stars. It's just very different to what we see in the solar system planets.
Of course. Okay. Um, Thank you. Now, Bob is asking, what if life is based on a different solvent system than water?
Yeah.
Say, uh-oh, I'm not a good chemist. Say, oh, I think I mean H2S, CO2, SO2. Would
Okay.
how would these studies evaluate this?
That's a great question. Yeah. So we're kind of making, or an assumption that we can make is that life on Earth seems to require water. That being said, that's not necessarily true. You can also imagine, life on Earth is carbon-based. What if it's based on something else? These are all very much sort of, to some degree, thought experiments that we can do, since on Earth we have sort of the life that we're familiar with. And what that, I suppose, would translate to in terms of observations of exoplanets is you might be looking for different biosignatures, right? You're looking maybe for different gases in the atmospheres of planets. That being said, I think it would be challenging to identify because you kind of would have, in order to, ideally, in order to sort of observe it in an exoplanet's atmosphere, we want to be able to compare it to an understanding that we have sort of in the lab on Earth. And since life here is based on generally like water as a solvent and carbon, that would be quite challenging to do. But it's certainly something that people think about and try understand because yeah, if life elsewhere in the universe formed completely independently of life on Earth, there's no particular reason that it would look like life does on Earth.
Hmm. Frankie is asking, is there a way to measure or detect radiation levels without sending a probe?
Um, so I guess I'm not quite sure what you're referring to, Frankie, but if you're referring to the radiation that a planet gets from its host star, we can calculate that based on the properties of the star and the properties of the planet, the distance from its host star. So we don't need to send a probe for that. Um, if we wanted to get like really get a granular understanding of the radiation that is incident on a planet's surface, then yes, we would need to send a probe, but that's very, very far beyond our capabilities, even within the solar system mostly. So that I don't think that's really feasible in the near future.
Paul is asking, given you estimate that every four stars has one planet in the Goldilocks zone,
Mhm.
and there are billions of galaxies with billions of stars in each, there are a lot of potential Earths out there,
Mhm.
right? Is he right?
Yes, yes, absolutely. I will say that right now we are limited to detecting planets in our own galaxy, in the Milky Way. That being said, I don't see a reason why, we wouldn't expect planets to form in other galaxies as well. We're just not really able to detect them. But yeah, no, that being said, we're really kind of on the cusp of being able to detect planets in the habitable zone. And we're sort of we've gotten there somewhat, but really on a large scale, we're sort of pushing that envelope at the moment. And so yeah, in theory, there are loads of these out there, which is really cool.
Keeps all the astronomers busy.
Yes, certainly.
Warren is asking, how do you view multi-planet systems?
That is a great question. And actually, that's kind of what my research is predominantly on. I mostly study multi-planet systems. I think they're fascinating and really allow us to probe multiple examples of planet formation in one environment. We know that, for example, all the planets in our solar system, we know that they all formed from the same material and have all orbited the same star for their lives. And so that lets us sort of almost break a lot of, like, compare things more directly. So do people call it comparative planetology, but really compare sort of these siblings and their impacts on one another rather than comparing, if you compare two planets around two stars, you not only have to compare the planets, but you have to take into account how the stars vary as well. So I think multi-planet systems are really very interesting and hold a lot of power for trying to understand how these planets form and
Hmm.
evolve.
And we're just a minute after 8. Let's conclude with Simon's question. He's wondering if any eco moons have been found yet, especially by Columbia University's David
Mhm.
Kipping.
Yeah.
Have I pronounced that right? David Kipping?
Yes. So exomoons are certainly a debated topic. There, as far as I'm aware, has not been conclusive evidence of any. That being said, I don't doubt that they exist if planets form in other systems in similar ways than they do in our own solar system. We know many of our solar system planets have moons, but if you think back to sort of what I said about how challenging it is to detect planets, and then you kind of scale that down to a moon, it's just really, really hard to do. And yes, David Kipping is sort of there. His research team does a lot of work on that. So yeah, that's kind of the place to look if you're interested in exomoons.
Columbia. All right. Well, thank you everyone for your wonderful questions. And thank you, of course, Emma, for spending an hour with us,
Yeah.
talking a little bit about your research and letting us know about the exciting field of astronomy and,
Yeah.
what researchers are doing in looking for habitable planets. And
Yeah.
I learned a number of things, but the Habitable Worlds Observatory. That I'd never heard about that before.
Okay.
So that
Yeah.
sounds quite exciting.
Yes, absolutely. Thank you all so much for your attention. I'll also just quickly take a note to thank my colleague Caleb Harada, who contributed to some of these slides. I meant to say that at the top and completely blanked, so I just wanted to acknowledge their work.
Well, thank you. Thank you, everyone. As I mentioned at the outset, this is the first of our talk. And next Wednesday at 7 o'clock, we are going to switch from astronomy to sociology. And we're going to be talking about the sociology of risk, crime, punishment, and public safety with Alicia McDonald, who did her undergrad at McMaster. And she is almost done her PhD. She's a PhD candidate and she's going to be talking about that topic. So if you're interested in sociology and crime, then we hope that you'll want to pull out your phone, scan the QR code, and register for that. So thanks everyone, and of course thanks to BMO for sponsoring our talk this evening. We appreciate Emma's time, and we appreciate your time too, the audience, for joining us. Thanks everyone. Take care, and we'll see you next week. Bye now.